In this lecture, we will introduce high-level programming languages. Recall that we talked about the assembly language and the fact that this was a much better way of writing programs compared to writing our programs in using machine language. But even though it's an improvement from writing code in machine language, there are still problems with the assembly language. One problem is that the programmer must manually manage the movement of data items between and among the memory locations and registers. So, we could give data items names. We could assign names to them, but still, we have to manually manage the movement of data. The programmer must also take a microscopic view of the task, breaking it down into tiny subtasks at the level of what is going on in individual memory locations. So we can't really look at what the problem is trying to solve. The programmer has to take care of all the inner components of the problem, actually dealing with the nitty-gritty details of the task, such as moving things around, dealing with individual memory locations. Another issue is that an assembly language program is machine-specific. So if you write an assembly program for one machine, you may have to write a completely different program to do the same task on a different machine. And then finally, statements are not natural language-like. Now, some operations kind of sound like it, but it's still not where we want to be. So, like, for example, the word store does not sound like a natural instruction to us. We would like to overcome these deficiencies, and this is where high-level languages come to play. They were developed to take care of the issues that assembly languages had. So thus we have the following expectations of a program that's written in a high-level language. So first, the programmer doesn't need to manage the details of the movement of data items within memory or even pay any attention to exactly where those items are stored. The programmer can take a macroscopic view of the task. So thinking of it at a higher level of problem solving. So like, for example, we can say add B and C and then call the result A. You don't have to worry about where B and C are stored. We don't have to worry about where A is stored. We don't have to worry about putting stuff in registers. So the primitive operations uses building blocks and algorithms can be much larger than what we're already used to. Programs should be portable rather than machine specific. So if I write a program on one machine, it should be able to work on another machine without really making that many changes or any changes at all. And then finally, the program statements themselves should be closer to the natural language and use standard mathematical notation. So these high-level programming languages are often called third-generation languages. And this just reflects the progression from machine language, which would be the first generation, to assembly language, which was the second generation, to the high-level language. Now, there is a problem with these high-level languages. Because we're making them easier for us to understand, the machine has no idea what these languages do. They have no idea. So what we need to do is to come up with a way to translate these high-level languages back down to our object code so that the machine can actually understand that. So it means we need another translator to convert our high-level language into these machine-level instructions. Now, we did have the assembler that worked for assembly-level languages, but that's not going to work for these high-level languages. Now, we do have a piece of system software which is called the compiler. And what the compiler will do is it will translate the source code, which is the code that's written in the high-level language, into assembly code, or at least some form of low-level code that's close to the machine language. And then they would have the translation be done to possibly a second translator, which could be the assembler, or it could be some other type of translation approach, but we would convert the assembly code down to the object code. And so, compilers for some high-level languages would generate low-level code that is machine-specific, but that's fine, because it would just still be very easy to convert the final object code for any particular machine language. So we're not too worried about that. We would have the compiler designed for each type of machine, but the high-level language would still work on any machine, so we wouldn't have to rewrite the source code. Now, some tasks would need to be performed often as part of solving other problems. Now, the code for these tasks can be written as a group of high-level language instructions and then thoroughly test it to make sure it's correct. Then the object code for the task can be stored in what's called a code library. So the whole point here is that the program can just request a copy of this object code and include it along with its own object code. So that way, for any tasks that are been done before, we can just get the code for doing those tasks again. We don't need to rewrite that code. There's another piece of system software that's called a linker, and this would insert the requested object code from the code libraries into the object code for the requesting program. So the linker would actually allow us to add the code from these libraries into our programs. And then the resulting object code is often called an executable module. And thus, a high-level program might actually go through several transitions in order to get the final product. Here is a diagram that just illustrates the translation process, just so you have an idea of what's involved. And as we're going to see here, the compiler has a much tougher job than the assembler, because the assembler was just an all-for-one translation task, because we just convert the assembly language instruction into machine language, whereas a compiler does a lot more. So we start with our high-level language program, so that's way up right here. So it first goes through the compiler, and it will be converted into an assembly language or some other low-level code. It'll then go through the assembler, which will then convert it into the object code that's in that specific machine language. We then would call the linker and include any library object code that the high-level language requested. So we put those together and we would get the complete object code. So we get our final program. But even then we're not done, because we still got to actually run the thing. So we would use the loader, which would take this object code and store it into our main memory. So it's going to be loaded into memory somewhere. And then we would have the hardware actually execute each line in the object code, and we would finally get the results of our program. Most of today's popular high-level programming languages fall into the same philosophical family. These are what we call procedural languages. These are also called imperative languages. So the idea is that a program written in a procedural language consists of sequences of statements that manipulate data items. So the programmer's task is to devise the appropriate step-by-step sequence of imperative commands. And these commands are instructions in that programming language. So we come up with these step-by-step sequence of commands that, when carried out by the computer, would accomplish our desired task. And these procedural languages do follow from the von Neumann architecture that we've talked about before. Because remember that was the architecture that was characterized by the sequential fetch, decode, execute cycle. So a random access memory would store and fetch values to and from memory cells. So it makes sense that we would design a language where the most fundamental operations are storing and retrieving data values. So while we have these high-level instructions, we're still storing, manipulating, and retrieving values. So let's just take a look at some example code here. So here's 2 lines of a high-level language code. So this A equals 1 with a semicolon just simply means that we're going to store 1 in location A. Now, A itself is not necessarily a memory address, but it is a name that's associated with some memory cell. And then we have C equals A plus B. So this means we're going to retrieve the values of A and B. We're going to add them together, and then we're going to store them in C. So even though a high-level programming language allows the programmer to think of memory locations in abstract rather than in physical terms, the programmer is still directing, using program instructions, every change in the value of a memory location. Now, the examples of these high-level procedural languages that we're going to discuss about are Ada, C++, C#, Java, and Python. And I mean, these are all high-level languages, but they differ in several ways. They differ in the rules, which we call the syntax, so that the rules of how the statements are written. And they also differ in the semantics, or the meaning of the statements. But it is worth mentioning that all these languages have the same underlying philosophy and model. So while there are differences in how they look and differences in how some of these operate, they're still doing the same things.